All right, today we're talking about how to build a reusable blueprint for your code. We're diving into a really useful design pattern that's all about getting rid of repetitive code and making your algorithms way more flexible and easier to maintain. And that pattern is the template method. So let me ask you something. Have you ever had that feeling of déjà vu while you're coding? You know, you write a block of code and then maybe a week later, you find yourself writing almost the exact same thing again, just with a couple of tiny tweaks. That whole copy, paste, and pray cycle, yeah, that feeling, that's a huge sign that there's probably a much better way to structure your work. Okay, let's make this concrete with a real-world problem. Imagine you're building a data mining app, and its main job is to slurp up data from all kinds of different documents. PDFs, Word docs, CSV files, you name it. For each one, it has to extract the data, run some analysis, and then spit out a standardized report. Now here's the catch. Opening and parsing a PDF is totally different from parsing a CSV. But the analysis part, the reporting part, that stuff is exactly the same for every single file. And that right there leads us to a super common problem in programming. How do you deal with the parts that are different while efficiently reusing all the stuff that's the same? Well, the first instinct, the sort of brute force way to do it, is exactly what you're probably thinking. You build a class to handle Word documents. Works perfectly. Then the boss says we need CSV support. So what do? You copy the entire DOC class, paste it, and just swap out the parsing logic. Then you do the exact same thing all over again for PDFs. And what's the result of all this? A total maintenance nightmare. The code for analyzing the data, the part that's supposed to be identical, is now duplicated across 3 different classes. So if you find a bug or you need to tweak the analysis logic, you have to remember to go and change it in 3 separate places. That is just asking for trouble. It's inefficient, and it's a recipe for bugs. But this is exactly where our design pattern swoops in to save the day. It gives us a blueprint, a really elegant, structured solution for this exact kind of problem. And that solution is the template method. So what is it really? Well, it's what we call a behavioral pattern. The main idea is that you define the skeleton of an algorithm in a base class. Think of it as the high-level structure. Then, the subclasses, the ones that inherit from it, they get to fill in the specific details for certain steps. But, and this is key, they can't change the overall flow of the algorithm. The superclass is in charge. So how does it actually pull this off? It's pretty clever. You take your big algorithm and you break it down into a series of smaller steps. Each of those steps becomes its own method. Then, you have one single template method that calls all of these little step methods in the right order. And that template method is the part that's set in stone. It's kind of like the Hollywood principle, Don't call us, we'll call you. The base class is the director, and it calls on the subclasses methods only when it needs them. Now, the real flexibility here comes from how these steps are defined. They basically come in 2 flavors. First up, you have your abstract steps. These are the mandatory parts. Every single subclass has to provide its own version of these, like the specific code to parse a PDF. Then you've got optional steps. These come with a default implementation, a fallback, but a subclass can choose to override it if it needs to do something a little different. Okay, I know this can still feel a little abstract when we're just talking about code. So let's use an analogy to make this crystal clear. I want you to think about building a house from a standard architectural plan, right? This blueprint, it defines the core sequence of construction that every single house has to follow. That's your template method. It makes sure every house is built to the same quality standard. So the blueprint is going to dictate the fixed steps. You have to lay the foundation first, then you frame the structure, then you install the plumbing. That order is totally non-negotiable. But the blueprint also leaves room for customization. These are the optional, overridable steps. The new homeowner gets to decide on the wall colors, the type of flooring, the light fixtures. See? The overall process of building the house doesn't change one bit, but the final product gets its own unique personality. So that's the big idea. Now let's bring it back to the code and see what this actually looks like in practice. Let's imagine we're working on a video game AI. We'll have a base class called Game AI, and inside it there's a template method called turn. This method lays out the law for what every AI does on its turn, in order. First, collect resources, then build structures, then build units, and finally attack. Okay, so now we create a couple of specific AI types that inherit from our Game AI. We've got an Orcs AI, it's aggressive. So for its build structure step, it builds farms and barracks. But then we have a Monsters AI. It's totally passive. So when it's time to build structures or units, it just does nothing. It overrides those steps with empty methods. The key here is that both of them are running the exact same turn template method, but their actual behavior is worlds apart because they've each filled in the blanks differently. But wait, there's one more really cool feature we can add, something called hooks. A hook is basically an optional step that's empty by default. It's like a little placeholder you can stick into your algorithm. For example, you could put a hook called before attack right before the main attack step. Now, most of your AIs would just ignore it, but a special berserker AI, it could override that hook to, say, trigger a rage mode just before it attacks. It's a way to add extra specialized logic without messing with the core steps at all.
Okay, so this all sounds pretty powerful, right? But like any tool, it's not a silver bullet. It's not the right fit for every single situation. So the big question is, when should you actually use it?
So let's look at the trade-offs. On the plus side, the big win is that you pull all that duplicated code into one place, and you give other developers a really clear way to extend your algorithm without breaking it. But it's not all sunshine and rainbows. The biggest downside is that the structure can be pretty rigid. You're locked into that skeleton. If your template has a ton of steps, it can also get really complicated and hard to maintain. And you do have to be careful not to violate certain design principles, like the Liskov substitution principle, especially if subclasses start doing unexpected things, like completely nullifying a step.
So here's the bottom line. You want to reach for this pattern when you have a well-defined algorithm, but you need different ways to implement some of its specific steps. It's an absolute game changer when you spot several classes in your codebase that have almost identical logic with just a few small differences. The whole point is to let people plug into your algorithm's extension points, not to have them rewrite the whole thing from scratch. At the end of the day, the template method is all about spotting a common workflow and formalizing it into a reusable blueprint. So, the next time you find yourself about to copy and paste a chunk of code, stop for a second and ask yourself, is there a hidden blueprint here just waiting to be found?